Okay, so here this partial y1a. So we want to translate this quantity into well, here this a is abstract index, but we want to write this quantity as a component index convention in the convention that a is a component index. So then this is clearly delta a1 is because this guy is just a coordinate basis. So in components, this vector is just delta a1. When a equals to 1 is 1. When a not equals to 1, it is 0. So this is delta a1. This is just a component of this vector. Okay. So then in this way, we translate a from abstract index to a component index. All right. So now we have the result for functional derivative of holonomy. So this is result for functional derivative of holonomy. So now we can just plug it in. So pj e closing bracket with h e. Well, I mean, if these two e's are different, so before we compute, so we should compute e prime, e prime closing bracket. But well, if these two edges are different, then well, you don't have any well, you don't have any contribution because so they depend on completely different set of fields. Okay, so which means that we only need to consider PE and HE. So we only look at exactly this setup. Otherwise, suppose this edge and phase, they are completely independent, then you see you are making functional derivative. Look at this. Look at this formula. So you are taking functional derivative of EX and AX at the same point X, but suppose they have no intersection. Holonomy and flux has no intersection. You don't find E and A at the same X. So we only need to consider that E, the surface and holonomy has one intersection. Okay, now we plug in the formula, plug in the result we just got. B3x 1 theta delta 1a. So this is, so firstly, this is functional derivative of flux. Well, and also we have a delta a1 coming from here, coming from this holonomy functional derivative, and you have delta x1, delta x2, delta x3. So delta x2, delta x3 coming from holonomy, functional derivative of holonomy, and delta x1 come from here, functional derivative of flux. Yeah, so here we exactly get a three-dimensional functional derivative. And we have trace. So this is coming from flux. Rho E x tau I H rho E x. Okay. And we also have contribution from functional derivative of holonomy. This is 0 x j tau I H x1. Okay, so here II is summed, right? And AA is summed as well. And this part, this is just give 1. So 2 deltas just give 1. Well, here, these three x, you can integrate our delta function and you set up x, well, x equals to 0. So this delta function restrict to x, vector x equals to 0. Well, it means that it's supported at the origin, right? So because this x1, x2, x3 are still evaluated in this coordinate, in this y. Although I call it y, I label this coordinate y, but I don't want to use y anymore because I have used x. But since we restrict everything in this coordinate, so this x is also the number. Well, for example, this x means the arbitrary point, but the component of this vector x is just the evaluation of this point in this y coordinate. Okay. So which means your delta function is supported at x equals to 0. It means that if you integrate our delta function, you have to evaluate your integrand at the origin of the delta, at the origin of these coordinates, which means you have to evaluate your integrand at the intersection point P. Okay, and when you evaluate the x at the intersection point P, so this holonomy is just this holonomy rho E x. It is just the rho. This is just HE1 because this rho E is a path starting from the source of the edge and then traveling through E1 to the intersection point, and then following the path system to an arbitrary point on the surface, right? And this is something we learned last time. So now x is just intersection point. It means that H rho E is just HE1. So this is HE1 again, HE1 inverse. This part is HE1 inverse. And here, well, it is the notation is maybe a bit confusing. X equals 1, it means, well, it's proper to write x equals to P. Probably this is better. If your delta function is supported at the intersection. And so here it is just H0P. Well, H0P is again HE1. Yeah. And HX1, P1 is HE2, right? So here 0, 1 is not really 0 in the coordinate y. Remember, this 0 is the parameterization of this edge. Yeah. So from 0 to point P, it's just E1. So suppose here it is the intersection point. Then from 0 to P is just the first part of the edge, and then from P to the end of the edge is just E1, E2. Okay, so now we can write explicitly, simplify this formula, integrate our delta function and taking integrand evaluate at the intersection point. So what we got is minus kappa over 2 trace tau J H1 tau I E1 inverse HE1 tau I up HE2. All right, so simplify get well, it simplifies the formula, but still you can see that you have this factor. Yeah, you want to relate the result in the theorem, you have to compute this factor. How to do that? So you see that HE1 tau I HE1 inverse, you can see this is just a joint representation on the Lie algebra, from Lie group to the Lie algebra, because here HE1 belongs to SU2 and tau I belongs to the Lie algebra SU2. So this is just a joint action. And well, or you can just try yourself using two SU2 matrix, sandwich a Pauli matrix. And what you get is just a linear combination of Pauli matrix. Yeah. So I think in quantum mechanics you also learn the same result. This is just a linear combination of Pauli matrix. Pauli matrices. Yeah, so K from again 1, 2, and 3. So here's tau equals minus I sigma, and sigma is Pauli matrices. Okay, And here also you know that this lambda, this matrix lambda, is a 3 by 3 matrix. 3 matrix. Lambda, it belongs to SO3. It's a 3-dimensional rotation matrix. So, well, I think this is also probably you should have learned in quantum mechanics, is that you make a unitary transformation of your spin operator, and what you get is a rotation in the space. Yeah, so this is nothing but this statement. So this tau I, this is just your angular momentum operator represented in the spin space, in the spin 1/2 Hilbert space. And this H is SU2. It's just a unitary transformation of your spin 1/2 Hilbert space, 2-dimensional Hilbert space. And this unitary transformation act on your sandwiching your spin operator, your angular momentum operator. It just gives a SO3 rotation of your angular momentum as a vector. So here, this formula states the same thing. And this lambda is just a 3-dimensional rotation matrix. All right, so let's use this formula to simplify our result. What you get is this minus kappa divided by 4. Because this is a linear combination of Pauli matrices of taus, you can pull out coefficients from the trace. Okay. And lambda L L H1. Well, here it is because I did the same transformation in the factor after. So because this factor can be written as, well, I just insert in HE1 inverse and HE1. This is just what I did. And then replace HE1 tau I, HE1 inverse by this formula, by lambda IK tau K. Okay. And you can see this is just the HE, right? And now for this trace, it's also very easy to compute because tau is just minus I sigma. We know trace of sigma I, sigma j is 2 times delta ij, and therefore, right? Therefore, so here it's just minus I, so this trace just gives minus 2 delta jk. All right. So right. So now we can further simplify result. Oh, you don't have minus anymore. Okay. Lambda IL. Okay. Let me see if my index is okay. JK. So here it should be J, IJ. It's not IK, IJ. Then tau L, HE. Okay. Now, but this factor actually equals to delta JL because lambda is a SO3 matrix. So being SO3, by definition, you have lambda IJ, lambda KL, delta IK equals to delta JL. Okay. So this is the definition of SO3. Being a 3-dimensional rotation matrix, it preserves the Euclidean metric. So delta IK is the 3-dimensional Euclidean metric, and SO3 being a 3-dimensional rotation, it preserves this metric. It leaves the metric invariant. And so this is the definition of SO3, and you just use this formula. You see that this lambda IJ, lambda IL is just a delta JL. Now you see you simplify the formula once again. It equals kappa tau half J, and then HE. Okay, and you compare with the formula, the theorem you get before, you find it's exactly the same. So kappa tau J divided by half, divided by 2, and then HE, you look at formula here. Well, this delta equals 1, tau half, kappa, and HE. Okay, and we get this formula number 2. All right. So any question about it? About this calculation? And then, well, to prove, this is your homework, to prove Poisson bracket number 3, which is the Poisson bracket between flux. P, K, E, P, K, E prime. Compute this. Well, so in case you have difficulty to compute in the intermediate steps, and there's a reference, and in the reference you can find the derivation of all those Poisson brackets. So this reference is HEP PH. It's the original reference for deriving these Poisson brackets. So 0, 0, 0, 5, 2, 3, 2. So go to this reference and you can find all the details of derivation. But I do encourage you first to try it by yourself. If you can't make it, you look at this reference. Okay. Any question about derivation? Okay. All right. Okay. Now we have our phase space on the lattice. Is, so I will call it P gamma. It depends on lattice gamma. It is just the cotangent bundle of SU2 to the power number of edges and modulo gauge transformation, quotient gauge transformation. Gauge transformation is SU2 to the power number of vertices. Okay. Well, and the symplectic structure or Poisson bracket on the phase space is given just by holonomy flux algebra. Poisson bracket on P gamma is holonomy flux algebra. Okay. Now, and once we have the phase space, we can proceed with quantization. So now let's come to quantization. So this is the starting point of loop quantum gravity. So, well, the idea is very simple. Remember, in quantum mechanics, our phase space is just two-dimensional phase space. Right? Phase space is just x and p. Well, it is well in mathematics, it is just phase space. It is usually called cotangent bundle of R1. So let's consider one-dimensional quantum mechanics. It's a cotangent bundle of R1, which is nothing but R2. All right, and with coordinate x and p, x is position, p is momentum. Okay, and then when you do the quantization, you just promote x and p to be operators on some Hilbert space, right? And the Hilbert space is isomorphic to the L2 Hilbert space, to the square integrable functions on R on your position space, right? And then any wave function psi will be just a function of x. Okay, because you have phase space and you can you know what is x, what is p, and then once you know what is x, your position variable, and you can define your wave function just functions of x, of position variable. That's your wave function. And your quantization, you promote x and p to be operators, then x operator x on phi of x is just a multiplication operator, and p hat x on psi of x is the derivative operator, which are partial x, psi of x. Okay, so this is your quantization, and you get x and p commutation relation equals to I h bar, Poisson bracket between x and p. Yeah, so which is just I h bar times 1. Yeah. Because Poisson bracket between x and p is just 1. They are conjugate variables. Yeah, so this is what you have done in quantum mechanics for quantizing your phase space. Okay, and here we are going to do just a very similar procedure. You see, we have our phase space, and we know conjugate variables. They are just holonomy and flux. And then our wave function, we can define wave function. Wave function is just a function of holonomies. Wave functions are functions of holonomies. Holonomies on let me say function of all holonomies on your lattice gamma. So which means your lattice has many edges, and you should take into account all the holonomies along all the edges, and functions and to be variables of the function. And the function is the wave function is just function of all those holonomies. And let's call this wave function f. So it's a function of all holonomies, he1 to he number of edges. So include your variables include all holonomies on the lattice. Okay, and now your Hilbert space are just built by this function. Hilbert space. So at this moment, I will define the Hilbert space I called H0 gamma. You will see the reason why I called H0. So this is just L2 function over SU2, and with some measure called Haar measure, because you define square integrable function, it depends on measure, and to some power, you have because you have many copies of holonomies on the lattice, so you to the power of all the number of edges, because for every edge you have one holonomy and you have one Hilbert space, and then you have to make a product, tensor product of all those Hilbert spaces on all different edges.
Excuse me.
Okay.
Why in quantum gravity we make the choice to take the holonomies as the variable?
Oh,
instead of the fluxes.
All right.
For example.
Okay. So it is your choice. So you can view that it is just historically convenient. Well, people use that from the beginning, so people find it is convenient. And indeed, people have studied. Also, suppose we use flux as a variable. Yeah, and there are work on that. Although it is not very convenient. That's the reason. Yeah, in some discussion, maybe that is convenient, but in many cases, it is not very convenient. Well, but different people have different views. Let's say why sometimes it's not convenient. The reason is that flux is not commutative.
Yeah.
It is just because flux they are not commutative. If you quantize this Poisson bracket into commutators and p, they are not commutative. But holonomy is commutative. Yeah. So suppose you say your wave function is a function of holonomy, then this function is defined on a commutative. It's defined on a commutative space. Yeah. But suppose you want to define your function as a function of flux, it's fine. But but the function should depend on a non-commutative space.
Okay.
So
And
it caused some inconvenience in some discussions, but some other, there are some people like it.
yeah,
it's not.
And so the path representations are not strictly equivalent, or it's just harder to find the same results?
In principle, it's completely equivalent.
Okay.
Yeah, it's completely equivalent. And there was probably in this class, I'm not going to discuss very much about it, but there's a theorem called, well, this is a unique theorem about representation for this algebra in loop quantum gravity. Well, in certain sense. So there is some unique theorem saying that suppose you want to define a diffeomorphism invariant theory, and then the representation of this algebra, it's unique. It's unique.
Okay, thank you.
Yeah. All right, and this Hilbert space H0 being many copies of smaller Hilbert spaces on SU2 is also equivalent to the L2 of a bigger space SU2 to the power gamma, and also the measure Haar measure. I will explain what is Haar measure in a moment. To the power gamma. So it means tensor product measure and product space. So because on each edge you have a holonomy, so the entire space of holonomies are SU2 to the power E gamma. Okay, and then you can just build a L2 space over this product space, and this is your space of all your wave functions. So Hilbert space. So F. So this F belongs to H0. Okay, so this is your Hilbert space, and as I said, and this H, d mu H is called Haar measure. So it defines the integration on SU2. So L2 SU2 d mu H. This is a square Hilbert space of square integrable complex valued function on SU2. Right. Well, this SU2 is just isomorphic. It's diffeomorphic. It's the same manifold as 3-sphere. So if you're familiar with Lie group, you know that SU2 is being a manifold. It is just a 3-sphere. Right? SU2 being a Lie group is a manifold having group structure. It is same time a manifold and also a group. The manifold for SU2 is just a 3-sphere. Okay. Well, what I mean by square integrable is that for any F1, F2 belongs to this Hilbert space. Let's consider just L2 single copies of SU2 mu H, and square integrable means that the inner product F1, F2 defined to be integral mu H is Haar measure F1 H 2 H, well, I have the complex conjugate, and this is integration is on space of SU2, and this integral must be finite. Yeah, so it means the square integrable just like what you learn in quantum mechanics. So this defines the inner product of Hilbert space, and well, the norm is suppose S1 equals F2. It just gives the probability of this wave function. Yeah. So well, so both of them, F1, F2 are functions on SU2. Okay, so how should we write this integral more explicitly? So okay, so what is so it's also I'm going to define for you the Haar measure, the Haar integration. Yeah, so this quantity. So let me do a parameterization. Let's parameterize SU2 using Euler angle. So this is some very basics about SU2. So because SU2 is just a 3-sphere, and so it's a 3-dimensional manifold, and it has 3-dimensional coordinate. So it can be parameterized by 3 parameters. And also SU2 is just some kind of rotation. So it should be represented, and it can be represented by using Euler angle. It should be parameterized by using Euler angles. So let me parameterize the group element of SU2 using Euler angles. Try H belongs to SU2 in this manner, e to the alpha tau 3 divided by half divided by 2, e to the beta tau 2 divided by 2, e to the gamma tau 3 divided by 2. Okay, so tau 1, tau 2, tau 3, they are just Lie algebra generator proportional to Pauli matrix. And here alpha, beta, and gamma, they are angles. They are actually Euler angles. Okay, so you can see that this H is just a composition of a rotation along the z-axis, and then a rotation y-axis around y-axis, and then a rotation around z-axis again, so which is exactly the Euler rotation. So we can make this parameterization for any group element of SU2. Now we can write this integral explicitly using those parameters. Okay, so then for any function on SU2, f of h, it can be written as a function with respect to these 3 angles. Gamma. Okay, and then the Haar integral mu h f h is 1 over 8 pi cube integral 0 to 2 pi d alpha 0 pi sine beta d beta and 0 2 pi gamma alpha beta gamma. Okay, so this the range of integration is also the domain of definition for alpha beta and gamma. So alpha beta gamma, they have a range of they have certain range. So alpha is from 0 to 2 pi, beta is from 0 to pi, and gamma is 0 to 2 pi. Okay. Okay. So now this is the Haar measure. This is Haar integral. So this gives explicitly how to compute this integral, and how to compute what. And it's also clear that what I mean by square integrable function. Yeah, so this is on a single SU2. Well, there's also some speciality of this Haar measure. So why we use Haar measure all the time on SU2? The reason is that it has a some nice invariance. So Haar measure is the unique measure on SU2, satisfies certain invariance. Unique measure on any group. Let me put this way. Let's say given a compact Lie group. So because Lie group is a group and it is also a manifold, so you can talk about the compactness of the Lie group. So in case that the manifold for this Lie group is compact, then this is called a compact Lie group. And this theorem is valid for compact Lie group. And for example, here SU2 is a standard example for compact Lie group because the manifold is a 3-sphere. It is a compact space. So SU2 is a compact Lie group. And then on any compact Lie group, there's a unique measure on this group G. So let's call this group G such that you have this. Firstly, you have normalization because the group is compact. You can normalize your integration equals 1. The volume of the group using this integration is just 1. And secondly, you have so this is first point, and second point is that it has certain invariants. Suppose you consider an integral on the group of a function, and suppose you translate this function using group multiplication, you get the same integral, same result. So this h multiply g. So you replace the variable of this function by from h to h multiply a arbitrary group element g. So for any g belongs to capital G, yeah, and then this, but the integral is not changing. So integrating this f using Haar measure is the same as integrating f h times g. Yeah, so h, so this f h times g is usually called a right translation of this function. Yeah, you can also multiply the group element from the left. It is called left translation, and this is also invariant. The integral also invariant. H. Okay. And moreover, if you take the inverse of the h, it's also invariant. Okay. And here for any f belongs to, let's say, continuous function on G. So C of G means continuous function. Okay.